Start recording. There we are. I can post that to my YouTube later. Don't do that. Minimize. Alright. Alright. I'm gonna post it to my YouTube. I'm gonna post it to my YouTube later. So then you can get it for all eternity. Or for as long as YouTube exists. Alright. So floating back up here to the top. So the BSA teaching method is that we explain what we're doing, demonstrate what we're doing, guide you through doing the thing, and then enable you to do whatever it is we're doing. I'm pretty good at the first two, explaining what we're doing and demonstrating it with a problem. So we have the equations that I care about to this point so far have been the linear equations, the four linear kinematic equations, these guys here. X is equal to x naught plus v naught t plus 1 half at squared all the way down to x minus x naught equal to 1 half v plus v naught t. And then Newton's law right here. The sum of forces acting on a thing is equal to the mass of the thing times its acceleration. Okay. And then there's the rotational version. That works just the same. The math is identical. The only thing that's different is the fact that instead of going in a straight line, now it's going in circles. So we have four rotational kinematic equations that work just the same as before. And then we have that the sum of torques is equal to I alpha. I comes from the table of shapes, which may be calculated if you are so inclined. That is above the grade, as I said before. That's above the pay grade for this class by a long ways. But if you're importing a singular torque onto the thing, you can torque has to come from somewhere. It's a force of some kind. So it's going to be a force times the distance from the center of what is rotating times the sine of the angle between the F and the R. And then there is a relation between the linear versions and the rotational versions. They're related by the radius of the circle, whatever that circle is. And so I was about ready to demonstrate how one might apply these equations to this particular problem, where we had a similar one last Wednesday, where we just had the one shape, where we had the one block on the right. This time I'm going to make two blocks, so we actually have a sum of torques adding here. Alright, so. And that's why we are here instead of in the classroom. Alright, so we'll make this guy here M left, and we have an M right, and we'll give this guy a big old M. Let's make it not a disc. Let's make it a cylinder of sorts. With something like, let's try this again. There we go. Oh dear. We're out of space. Alright. So, he's got mass M. He'll have a radius R outer and a radius R inner. Did I say left and right? I did. Okay, apparently. Alright. So, we'll put in some numbers here for this shortly, but the things I would like to know, I would like to know the tension in the string on the left, the tension of the string on the right, and the acceleration. I think that'll be, let's get the angular acceleration. Just make sure that we have no, we don't need to do that. Acceleration should be enough. Those are the things I want to know. Alright, mass on the right. Let's go with 5 kilos on the right. And we'll do 2 kilos on the left. Let's make this pendulum, this pulley up here. Let's make him a 1/4 kilo. like so. There we go. Radius for the outer, we'll go 10 centimeters, which is 0.1 meter, and inner it will be 5 centimeters, 0.05 meters. All right. All right. So the steps that we need to do here. Number one. Diagram of forces on each part. 2. Write equations. Not just forces, but also torques. Let's get rid of that. Forces and torques. And there's extra buttons on my pen. Torques. There we go. Write equations for each part and direction. So in some cases we'll have like on one object we'll have forces going in the X direction and forces in the Y direction, or we might rotate a little bit and say something about the forces that are parallel to the surface and perpendicular to the surface. So sometimes there'll be 2 directions for some objects, not just in the case where we got 1, 2, 3, and each one of these has only one direction attached to it. And then 3, solve equations. For answers. And then 4, I would recommend, but do not require, an ID 10T check. Basically, if you were to solve this out, if you don't solve it out algebraically, it can be hard to do an idiot check here. The ID be something like, if MR gets bigger, does the acceleration in the direction this way get bigger? If you had solved it out algebraically rather than just punching in numbers and then solving, it would be easier to tell. Does a change in the input values produce a sensible change in the output values? Alright, so diagram. Alright, for the mass on the left, what forces do I have? What forces do I have here on my left? Well, for some reason, I tend to not get the interaction I like to have off of remote teaching. So we got the force up, we got tension on the left, and we got gravity on the right. For the mass on the right, the forces that I have going up, we have tension on the right and gravity going down. mg equal, damn. There we go. And then for the pulley, it's got here, if you get anything, this is MP, like so. Well, he's got a torque on the right and torque on the left. Torque on the left is from TL, and torque on the right is from TR. There we are. So, now we can sum these all up. I think I need a little more space. So, we have that the sums of forces on the left. We have that. So what I'm going to do here, I should also assign assigning directions. Come here. Directions. There we go. So I'm going to say up is positive on the left, down is positive on the right. So that means that on the left we have that TL is up positive minus mass of left G down is equal to mass left G, not G, A. And then the sums of forces on the right is going to be tension, no, not that guy. Down is positive on the right, so that's mg, m right G, minus tension right, that is equal to m right A. So the reason why I've done that is that there's a coordinate that goes with the rope. And so I've decided that the rope defining that coordinate on the left is up positive on the left and down positive on the right, so it's consistent. So if I were to stretch this rope horizontally, then its positive would always be to the right, but you know, it's being draped over this pulley here. So up on the left and down on the right is positive. Uh-oh. Alright. And then we can sum our torques for the pulley. Well, we got a T left. Oh, no, that's the wrong direction. This way is positive. So that means that TR. Uh-oh, one more. Yeah, no, we're good. TR times R outer minus TL R outer is equal to I alpha. Okay. So I got my torque on the right minus torque on the left. So now I have three equations and three unknowns. Almost three unknowns. This alpha needs to go away. So to get rid of that alpha, I need to invoke this guy here. So this becomes I A on R. Alright. Now I haven't provided you with the massive table that I is going to invoke yet. I is equal to 1/2 m R outer plus R inner, both squared. Try again. Square this one, R inner, square that one. There we go. Do I particularly care? Not yet. Might as well evaluate that. So that's 1/2 m quarter kilo our inner is 0.1 meters squared. Nope, not yet. Plus 0.05 meters in my space squared. Calculator, what is this value? 0.25 divided by 2 times 0.1 squared plus 0.05 squared. 0.00156. 0.00156 kilogram meters squared. These guys here. I'm going to solve both of these here on top for my TL and TR. So then this guy becomes TL, move that to the other side. TL is equal to ML A plus G. And this guy, I need the TR by itself. Move that over to the right side, move MA to the left side. So I have that TR is equal to MR G plus A. Right. Guy goes this way. Nope. G minus A. Where I say. Alright. Do an idiot check here real quick like. TL is going up. And so that means that if TL is going up, perhaps now's not the best time for this check here. What I really care about right now is the fact that TL is going up and TR is going down, but acceleration is going opposite because the L and R's are going opposite. But G's are both positive. So I'm hoping that makes perfectly good sense. Alright. So now I can take these guys and shove them to here. So now I have ML A plus G R outer minus T. Nope. I've messed that up. This is T right here, so I need this guy here first. MR G minus A. I probably should have been at this for about half an hour. It's longer than I should have liked, but we'll be fine. ML G plus A plus G, whatever. R outer. And that is equal to I A on, well, this would be R outer here, because that defines what's the acceleration. That's the point at which the acceleration and the angular acceleration are linked to each other. Now I can solve for A. That's going to be a pain in the behind, question mark. Yeah, not too bad. So, alright. Yeah. So we're going to take this guy here, this minus A, we're going to add it out. So I'm going to add to the other side. M R A R naught. And we're going to add this plus A with that minus there to get the M L A R naught. And we'll do it to the other side. And so we end up with that M R G R naught minus M L G is equal to I A on R naught plus M R A R naught plus M L A R naught. Not R naught. Those are our outers. R outer, R outer. Alright. So now I'm going to factor out this A and evaluate everything else. Alright. Calculator. On the left, what we got? MR is 5 on 5 times 0.1. Here. 5 times 0.1. Oh, yeah, left. And minus 2 times 0.1 times R times G. Whatever. 9.8. So on the left-hand side, I have that. So this is a kilogram times a meter per second squared. Meter per second squared. And so that's a Newton. And that's a meter. So this becomes a Newton meter. So this will be 2.94 Newton meters on the left side. And then on the right side, 0.001. So I just go back and get the previous value. Divide that by 0.1 plus 0.2. Nope. Times 2 plus 2 times. So M left is 2 times this R naught RO 0.1 plus MR on the right there, that's 5 times 0.1. And so that works out to 0.715 6. 1/6. Well, that's a kilogram there, and that's a meter there. So that's a kilogram meter. And then this guy here, that's a kilogram meter squared, but I've divided it by this R0 here, that's a meter. So it's kilogram meter squared per meter. So that'll work out to a kilogram meter. So that's a kilogram meter. And then my acceleration is the thing I'm looking for. So acceleration is 2.94 divided by Ains 4.12 meters per second squared. So how did that happen? So when I divide by the kilogram meters here to the other side, that meter cancels with that meter there, and then the Newton divides by a kilogram gets me back the meter per second squared, and I'll get me my meter per second squared. Alright, so we have an acceleration of 4.12. Yeah, 4 point. Come on. If we're going to do it, let's get rid of that question mark, because we know what the answer is. 4.12 meters per second squared. The sign says that we're headed this way. MR is headed down, the positive, which makes perfectly good sense because this side was positive going down, and the heavier side is 5 kilos rather than this 2 kilos here. So if the left side had been, say, 10 kilos, then I should be headed to the left down, and so it would have been a negative value. So the fact that my idiot check for this acceleration is the fact that I have a positive acceleration to go with my positive direction. Alright. Going to get rid of all of this here in the middle, because now I can answer what is T left and T right. So T left is equal to mass on the left was 2 kilos. Its acceleration was 4.12 meter per second squared. Oops. Plus gravity 9.8 meters per second squared. Calculator was this value. 2 times Ains plus 9.8, 27.8 newtons. 27.8 newtons. And T right was 5 kilos. Gravity 9.8 meter per second squared. Stop. Whatever it is you're doing. Meter per second squared minus acceleration 4.12 meter per second squared. So we get that is 5 times 9.8 minus 4.12. 28.4. Alright. 27.8, and let me erase my question marks. And then insert my answers. 27.8. Newton meter. Nope, just newtons. And 28.4. Alright. Does that make sense? Why these guys are so close to each other? So if my pulley had no mass, then it would take no effort to accelerate the pulley. Well, the difference in tension here is the force is the total force that became the total torque. Basically, I erased it right here probably. That became the acceleration for this pulley. So if my pulley had no inertia, no I to it, then it would take nothing to accelerate it, and these guys would be equal. The difference is what makes it accelerate when it has a mass. Alright. Questions? Make sense? I have demonstrated a problem. Let us see if we can't get y'all's to show me how it's done, so we can guide you through the process. Alright. Let's see here. Let's write down a question. Alright. What we got going on here? Yes. I like that one. Let's do that. Alright. Times is easy. That should be good enough. Alright, so we have a helicopter. Like so. It has on it, so it's moving forward. Here's my vertical axis here. This here. Boy. Vertical axis there. X is there. It is moving forward with some velocity. That is constant. It has acting on it. One moment. Alright, is acting on it. Some left L. That is theta from the vertical. Theta is 21 degrees. It has gravity acting on it. And there's some resistance to it. It has a mass equal to... No, it doesn't. It has a mass, but it doesn't tell us what it is. But it does tell us that the force of gravity acting on this thing is 53.8 metric tons. Better known to, nope, not metric tons. Newtons, that's what it's got. V is going for a constant. L is a lift. It's got some R resistance to it. The problem would like to know what is L, and what's the magnitude of L, and I would like to know R. Probably the magnitude of R, right? Alrighty. Oh. Who would like to show me how this problem is done? Would somebody like to show me how this problem is done? If somebody doesn't volunteer, somebody will be voluntold. Alright. This here. Where is my command line? Command line is presently missing. Command line. Fetch me Mathematica. New document. Random choice. Who do we got? We have Caleb. We have Destiny. We have Hannah. And we have Mary. Make random choice there, Mathematica. Before I figure out how to make a random choice. Oh, come on. There we go. Print screen. Copy that. And delete that. Paste that. And give me a motion. Thank you. Okay. Mathematica has kindly made a choice for me. Destiny, would you be so kind as to demonstrate how this problem is done? You are sounding great. You are sounding great. Alright, stop sharing. There we go. I dropped the problem so that you could share it. So you can share your own screen. Let me see here. I can bring that up here. Oh, that guy there. Allow. Alright. Come on. Alright, it's back. Okay. Try that angle again. Here. 21 degrees. There we go. Got it? Do I need to stop? Yeah, I can stop presenting so you can put it go. You got a camera? Is that what we're looking for? Yeah. Yeah. Well, it's Google Meet, so I'm not the most familiar with it either. I wanted to try to get a whiteboard on here, but he said, oh, and if you want people to interact with it, they have to install it themselves. I was like, well, I don't really care to do that, so we'll just do screen sharing or cameras, as the case may be. Well, you raised your hand. It's all right. Why don't you walk us through it? Show at least show me how it's done. Let me get rid of this here and delete that. Okay, let me put up the presentation. Put that back up. Grab. Where is it? There it is. Grab that one. Allow. Thank you. That's nice. Go away. So go away. You're presenting. Yes, very good. All right. So, what do I need to do here? Yeah, tell me what I'm doing here. Yep, it wants to know lift and the resistance. Or drag. More. Well, that... Yep. So, Let me clear off some of these other things over here. We don't need them. These guys here, we can go. You can go away. Alright. Alright, so what am I doing here? I got a box to represent our helicopter, right? So what forces are acting on it? You were saying? You know? Where are you seeing tension here? We got an L and we got an R. There's no T's on here. Where are you seeing the T? This is an L and this is an R. We also got this V here. V equals constant. What other forces do I have here? Well, they look and bite you. It's right there. R and L, right? Those two right there. So R is pointing to my left, right? Correct? Alright. R is going that way. What direction is L pointing? Up, or a little bit forward of up? Looks like it's... So we got y-axis here, that's up, right? But L is a little bit in front of up, so... Not just straight up, but mostly up, right? Correct? So... No, we're doing fine. So it's actually going and make a straight line, close enough. So that was going that way. Alright. Is that L useful to us in that state? Is L useful to us in that state? Yeah, because I mean, FG is pointing down, force of gravity is pointing down, R is pointing to the left, but L is pointing not in either of those directions. So might we want to do something to L first? Solving is not the word I would use. I would use the phrase breaking it into components, right? So L has a vertical component and horizontal component, right? So if L is pointing a little bit up, mostly up, but a little bit forward, then I would have then what components do I have from that L? So L is made up of an LX and an LY. Generally speaking, so is these guys here. So that guy there, he's got nothing forward and backwards, but he's just FG going down. Like so. And this guy, he's got just the R to the right, that's minus R, 0 here. So these guys technically have components to them, but there's 0 components, so we don't care about those. But this L guy, he's got an LX and an LY, right? Yeah? Yeah, so where's that LX pointing? X is horizontal. So Y is pointing up. Y can point up. So LY can point that way. But LX pointing which way? To the right, right? To the right, yeah. That way. Okay. Alright. So what equations do I have? So I've drawn my diagram of all the forces acting on this helicopter, right? What's next step? Yeah, writing down the equations. Alright, so then I can do a sum of forces, right? So, which one should I do first? Have I said anything about one direction or another being first? Or no, there's not. If you write down all the equations, then it doesn't really matter once you get them all written down, right? So we can do left and right or up and down first, right? So I got forces in the X direction and forces in the Y direction. Which one should I do first? You're the one driving here. I'm trying to let you drive. Sure, we can do X's first. All right. So, which force should I write down first and make it positive or negative? Which one? Well, so we're doing the X direction, so there's two forces in the X direction, Lx and R. And so I can pick one of those to be positive, one to be negative. I've kind of hinted at which one should be negative, but it doesn't have to be. So I need to sum my forces in the horizontal direction. So I have an Lx and a minus R, right? So, yep. No. That's jumping ahead there. This guy could be plus or minus, and this guy here can be plus. If the right side is plus or minus, then the right side can be minus or plus. And we're just summing these guys here in the X direction, Lx and R. Lx positive, sure, we can do that. Lx positive minus R. Alright. My velocity is constant, right? So what does that mean for my acceleration? Yes, but we can be more specific than that. What? Ow. Ow. So if I invoke my velocity formula, v is equal to v naught plus at. Well, that means that v minus v naught. Oops. Try again. There we are. V minus v naught is equal to at. Okay, well, v is constant. That means that v and v naught are the same, right? So v minus v naught means it would be equal to. Yep. And since time is progressing, that means that which of these two values must be 0? Yeah, my acceleration. So that means up here, my acceleration is 0, right? Yeah, meter per second squared. So this is equal to 0 times anything is 0. In this case, this is kilograms, and that's meter per second squared, so this is a Newton. Alright. So Lx minus R is equal to 0 newtons. Okay. What's going on with my vertical here? Which one? Ly or Fg? Sure. We make that guy positive, which should go nicely with that minus sign I've written down right there. So we have an Ly minus Fg, and the acceleration in the vertical direction is? He's hovering at constant elevation, which means his acceleration is 0. Because his velocity in the vertical direction is also 0, so that's 0 newtons. Okay? Okay. So, now we can solve a little bit. Now we can actually go to step 3. We can actually solve for our values here, right? So, which one should I solve for first? Could. That's not the worst idea possible. Let's California. Yeah, we can do that. Yeah, we don't need it right away, but it won't hurt. So, if I have that Lx minus R is equal to 0 newtons, I'm looking for L and I'm looking for R. Which of these guys should I put on? Well, I'm not sure it really matters. Who should I solve for? Well, we'll get to L shortly enough. Yeah, let's go for that R character. But, I mean, does it really matter? Add R to both sides, right? Like so. So that means that Lx is equal to R. Well, this guy is related to our L here. So we can't really make more progress to that because we don't know what Lx is because that's related to my L. I don't know what R is, so I can't make more progress to that guy. We'll come back to him later. These two, right? We need to solve for these guys. Alright, well, let's solve for them. Well, Ly minus Fg is equal to 0. I know what Fg is, right? What's Fg? No, this guy right here. Fg equals 53,800 newtons. So we know what he is, right? So what does that mean about? Yeah. So what does it mean by? What does it mean that Ly is? Solve this guy for Ly, right? So that means that we'll add Fg to both sides, and we get that Ly is equal to Fg. So we know what that is. 53,800 newtons. Okay. That's getting closer to what we need, but we still don't know what L is. However. Alright, so I have a triangle, right? I have an Ly here and an Lx here. So I'm going to draw that triangle again. There we are. Ly goes there. Lx goes here. I know this angle here to be theta. In particular, it is 21 degrees. Alright. So, now, alright, we can do some trig, right? What trig should I be using? I have the adjacent and the opposite, don't I? Well, that's not entirely true. I have the angle and the adjacent. I'm looking for the opposite, alright? Which of the trig functions has the adjacent and opposite? This here cosine is adjacent and hypotenuse Sine is opposite over the hypotenuse. And then tangent is, let's see here, opposite over adjacent, right? We gotta have better days. Alright, so tangent of 21 degrees is equal to what? Which opposite is what? Or the symbols, if we don't know what the number is. Opposite from this angle is, yep, and adjacent is, that's the angle. Ly is our adjacent. Yeah, there we go. So now I can solve for that Lx, right? So Lx is equal to, how do I get that Lx by itself? Yeah. So my Ly is here, and my Lx is here, and the Ly is here. So how do I move that Ly to the other side so I get my Lx by itself? What is the opposite division? So I need to multiply by Ly on both sides. So this Ly will cancel with that Ly. And we find that Lx is equal to, what's Ly? Oh, here he is. Here's my Ly. 53,800 newtons. Tangent 21 degrees. 53,800. Tangent 21 degrees. 20,700. Like so, right? Oh, well, I know what. Isn't there somewhere I needed my Lx? Wasn't there somewhere I needed my Lx right here? Yeah, so what does that mean my R is? There we go. Yeah. 20,700 newtons. Yep. Alright. So now we know everything about L. We know that it's, that is 20,700. Let's not put that there just yet. Newton. And 53,800 Newton goes there. Okay. So now I have both components of L. How do I turn those components of L back into the magnitude again? Isn't there a trig equation with somebody's famous name on it? No. Newton didn't do anything with trig. He invented calculus. But somebody invented a triangle identity and got their name attached to it. Supposedly. The problem is, it was actually a religious cult, and we're not entirely certain if the guy whose name is attached to it actually derived it, because they were so secretive and whatnot. Supposedly he wouldn't eat peas and stuff like that. one Pythagoras, yes? What is Pythagorean identity? What is the Pythagorean identity? I think it's what's the equation? Equation. Yeah, that guy. Yeah. So I have a A and a B, and I need the C. Okay. So that means that let me get rid of these question marks. Question marks. Go away. Oh, that one there. Alright. Alright, so let's make it here. That what? Come on. Other one. This one. Try again. So here we go. Square root of lx squared plus ly squared, because L squared is equal to Lx squared plus Ly squared. So it means that L is equal to all this guy up here. So let me evaluate that guy. Square root of Ains squared plus 53,800 squared. Execute 57,600 newtons. And this guy, well, we already know what he is, because his other component is 0, so that means that, well, 0 squared plus anything is, well, that anything. Square root that, and all. Yeah, we're back to where we started. So we're back to 20,700 newtons. And we're done. 5 minutes. That took a while. One more. Alright, given the fact we have 5 minutes left, I don't feel like continuing with these problems too much more. So let's see here. Let's see here.